as the title above shows, this is the third lecture in a series of advanced level problems on friction. We are going to discuss various problems on applications of Newton's laws of motion, taking into account frictional forces between rough surfaces. The problems are further marked by 1 dot, 2 dots or 3 dots to denote difficulty levels of 1, 2 or 3 respectively. So a bit of rearrangement in my writing. All the steps so far are shown on the right hand side here. And let us have a look at the question once again for the parts B and C. In the part B, they are telling to find relation between T1 and T2 for the case when the rope is actually slipping on the pulley. So let's do it first. I'm writing here only. Let's return to this step here. In part A, we have shown in case the rope is just about to slip on the pulley, I have used this relationship. So coming back here, when the rope is actually slipping on the pulley, this dF becomes equal to the corresponding force of kinetic friction, isn't it? So I modify this equation to write down, in case of actual slip, that dF now becomes equal to the force of kinetic friction, that is equal to the kinetic frictional coefficient mu k into the normal force, that is dN, which is giving me mu k into T into d theta. And using question number 1 above, since I have got dt is equal to df, moving similarly, I could write down that dt is coming out to be equal to df, that is mu k into T into d theta. And proceeding exactly in the same way as in part A, you can show yourself that eventually you get that T2 under kinetic condition is coming out to be T1 under kinetic condition multiplied by e to the power mu k into beta. That is my next important result, that I'm calling it Roman 2 in capital letters. So let's see what we have got. We have got when the rope is actually slipping on the pulley, in that case tension on the right side of the rope is equal to tension on left hand side multiplied by Euler's number to the power the product of kinetic frictional coefficient mu k and the angle subtended by the rope in contact with the pulley at the lattice center. So this is the part B's answer. Okay. Now what about part C? Looking at the question once again, they are telling here that suppose beta is 120 degree. The value of mu s is 0.500. If a force of 1 kilonewton is applied to one end of the rope, what minimum force at the other end will keep the rope stationary? I hope you have read the question. We shall use the data from here to do this numerical part. They have said the angle subtended by the rope in contact with the pulley at the pulley's center, that is 120 degree, but don't forget to convert into radian. This is coming out to be 2 pi by 3 rad, isn't it? The value of mu s, static frictional coefficient, is given to be 0.500, and the value of the larger tension, in my case that is T2, that is, well, this is T2s rather, this is given to be 1.00 kilonewton, that is 1000 Newton. And you have to find out the minimum permissible value of T1s so that this rope does not slip on the pulley, that is, it's just on the verge of slipping without slipping. So we recall equation number 1 from here, the result 1 rather, and the result 1 is giving us T2s is equal to T1s into e to the power mu s into beta. Putting the values, T2s is given to be 1000 Newton, T1s is the unknown quantity, E is the Euler's number. You can easily check it. Its value is about 2.72. Mu s is given to be 0.500 and the value of beta in radian, that is 2 pi by 3 only. So go for the calculation and show that the value of T1s is coming out to be about 351 Newton in 3 significant figures, and that is the answer of part C of the question. We conclude that this is the value of course, T1s. We conclude that with a minimum force of 351 Newton on one side of this rope, a tension of 1000 Newton on the other side of the rope can be balanced for this given situation. So let me highlight my answers. We have got in part A the condition between T2 and T1 for the case when the string or rope is just about to slip on the pulley. Then we got corresponding relation between T2 and T1 when the rope is actually slipping on the pulley. And in part C we got with a value of T1 Newton, minimum value, a tension of this, a tension of 1000 Newton on the other end of the rope can be balanced. Here are the answers of all the parts of this lengthy question.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.